In this video, we'll continue our lesson on propositional logic, and we'll be talking about propositions generated by a set and then the hierarchy for logical operations. Let S be any set of propositions. A proposition generated by S is any valid combination of propositions in S with conjunction, disjunction, and negation. Or to be more precise, if P is a proposition in S, then P is a proposition generated by S. And if X and Y are propositions generated by S, then so are negation X, X or Y, and X and Y. You'll notice that we didn't include conditional and biconditional in these definitions because these can be generated by the disjunction, conjunction, and negation operators, which we'll see later in our study of propositional logic. Now, it is customary to use the following hierarchy for interpreting propositions. Of course, if there are parentheses, they can override this hierarchy. The first is negation. So this is kind of like an order of operations. First we'll do negation, then conjunction, then disjunction, then conditional and biconditional. And we work from left to right. So for example, an expression like P and Q or R, because we know that we're doing conjunctions before disjunctions, that means we'll first do P and Q, then we'll do or R. Some more examples. P and Q and R can just be P and Q and R. First P and Q, then and R. Not P or not R. It's understood that we're negating P or negating R. Not P is the negation of P, and then we'll take the negation of that. And we can also use these rules to interpret longer strings like this one. P if and only if Q and R implies S. We'd first do Q and R, then implies S, and then P and if and only if Q implies S. Okay. One other quick note is that it's not necessary that a proposition generated by a set should include every proposition in that set. So if the set is P, Q, R, then it's still perfectly valid to say negation Q and R is generated by the set, even though it doesn't include the P. So let's do some exercises. First, we'll practice constructing truth tables. So we're asked to construct the truth table of P or not P. So I only have one proposition, P. That means my truth table will have two rows. I'm going to have P, then I'll do a column for not P, and then I'll do a column for P or not P. P can either be true or false. If P is true, then not P is false. If P is false, then not P is true. Then in our third column, we're doing disjunction or. That means if either of the first two columns is true, then the statement is true. So since I have P true, this is true. And since I have not P true, the second row is also true. So P or not P is always true. Next, we're asked to construct the truth table of P and Q, or Q and R, or R and P. And it's clear because of the way the parentheses are that we want to first do P and Q, as well as Q and R, as well as R and P, and then finally connect them all with ORs. Since I have three separate propositions, P, Q, and R, I'm going to need 8 rows in my table. So I'm going to make a column for P, a column for Q, a column for R. then a column for P and Q, a column for Q and R, a column for R and P. Then I can have a column that is just P and Q or Q and R. And finally, I'll have P and Q or Q and R or R and P. Now I know that I need 8 rows in my table, and that these 8 rows should represent all of the possible combinations of truth values for P, Q, and R. So the way that we'll order them is for P, I'm going to use blocks of 4. So I'm going to have true, 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 and then below that, false, 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 false. And remember, we could do these with zeros and ones as well, in which case that would be 1, 1, 1, 1, 0, 0, 0, 0. Then for Q, I'm going to do them in blocks of 2. So I'll have true, true, then false, false, then true, true, then false, false. And lastly, for R, I'm going to alternate every other one. True, false, true, false, true, false, true, false. And now you should be able to see that we have all the possible combinations. We have true, true, true. At the bottom we have false, false, false. But we also have every combination of 2 trues and 1 false, or every combination of 2 falses and 1 true. Now we're going to go column by column. First I'm doing P and Q, so I'm looking at these first 2 rows. Since it's and, I would need both columns to be true in order to say that P and Q is true. So in the first row, P is true, Q is true. That means P and Q is true. Similarly, in the second row, P and Q is true. But everywhere else, since I have at least 1 false, I'm going to say the rest are false. Then I'm going to look at Q and R, so the second and third columns. And the same rule applies. If they're both true, then I get to say it's true. Otherwise, if one of them is false or both of them is false, then it's false. So I have true, false, false, false. Here again, true, then false, false, false. And we'll repeat that process with R and P, columns 1 and 3. So I have true and true is true. True and false is false. True and true is true. True and false is false. False and true is false. False and false is false. False and true is false. False and false is false. Now, I need to do P and Q or Q and R. Eventually, I'm going to also do or R and P, but I'm going to do them in separate steps here. Since it's now or, I only need one of them to be true in order to say that it's true. So P and Q or Q and R, I have true and true. True or true is true. False or true, true or false is true. False or false is false. False or false is false. False or true is true. False or false is false. And we're false the rest of the way down. Finally, I'm going to combine this column and this column using disjunction or. So I'm looking in my last 2 columns and I'm seeing if I have true anywhere, then I get to say it's true. So true or true is true. False or true is true. True or false is true. False or false is false. False or true is true. False or false is false. False or false is false. False or false is false. So now I have my completed truth table for the compound propositional statement P and Q, or Q and R, or R and P. The next exercise asks us to rewrite with as few extraneous parentheses as possible. So it looks like I have negation, then I have P and R, and because they're inside this set of parentheses, that negation is applying to both of them. And then the whole thing is or S. But I don't need these interior parentheses around P, R, or S. And I don't need this larger set. So this is going to look like negation, P and R, or S. And that's plenty of parentheses for it to be clear, because we know that we do negations before we do disjunctions. I don't need further parentheses. Now looking at B, B looks like it should be P or Q and R or S, R or Q. Usually we will do the conjunction and before the disjunction, but because of these sets of parentheses out here, it's clear that I need to keep these grouped together, but I don't need the interior ones. So this is just going to become P or Q and R or Q. In this case, even though conjunctions take precedence over disjunctions, the parentheses allowed us to override that rule and say first we're going to do P or Q or R or Q, then we'll do and. Next, in what order are the operations in the following propositions performed? So for A, I have P and negation Q, or R and negation P. I have P or negation Q, or R and negation P. So negations come first, but then between the conjunction and the disjunction, the conjunction takes precedent. So first, I should have R and negation P. That's by itself and it will be preserved. Then I can do or negation Q and or P. So we note that this negation Q is happening before we do any ands or ors. So this is essentially what it would look like, with negation taking precedence over conjunction and conjunction taking precedence over disjunction. Now here I have switched these two disjunctions to conjunctions. So I have P and negation Q and R and negation P. So the only thing we have to remember here is that the negations happen first. So I would still just write that as P and negation Q and R and negation P. But I'd remember that the negations are happening first, and then I'm doing the conjunctions. Question 5, determine the number of rows in the truth table of a proposition containing 4 variables, P, Q, R, and S. Well, our rule of thumb was that we would need 2 to the power n many rows in a truth table involving n proposition. So since we have 4 here, the truth table will require 2 to the n 2 to the 4 equal to 16 rows. Now what if we're asked if there are 450 lines on a sheet of paper and we want to reserve one line for each line in a truth table, how large could the set S be, or the cardinality of the set S be, if we want to write truth tables of propositions generated by S on the sheet of paper? Now we did note that a proposition generated by a set doesn't necessarily have to contain all of the propositions in the set, but we want to make sure that this one piece of paper, we could use it for any. So we're going to say 2 to the n, because we know that's how many rows we need if the cardinality of S is n. And we want that to be less than or equal to 450. So it looks like I have an exponential inequality. How would I solve such an inequality for n? Well, I'd need to use logarithms. So I want to take log on both sides, but I need to ask myself if my sense of inequality is preserved when I take logs on both sides. And it will be, but that's because the logarithm is an increasing function. So if we remember roughly what the graph of the logarithmic function looks like, it looks something like this curve. This curve is always increasing. And because it's always increasing, I can apply this function. So I'm going to use natural log on both sides. And I get to say that the sense of inequality remains. But this would not be true if this weren't an increasing function. So it's very important when we're doing mathematics that not only are we thinking about these things, but we're also writing them down. So I have to say this is true since log is an increasing function. If it weren't an increasing function, then we could not solve this way. Now I'm ready to use my properties of logarithms. So I know that the natural log of 2 to the power n is the same as n times the natural log of 2. And I also know that the natural log of 2 is positive. So I can divide by the natural log of 2 on both sides. And again, I get to keep my sense of inequality. But again, these are the things we need to pay attention to. So since the natural log of 2 is greater than 0, that's the only reason that I can divide on both sides and maintain my sense of inequality. So at this point, I'll probably need to consult a calculator and say natural log of 450 divided by natural log of 2. So n is less than or equal to 8.138 rounded to 4 decimal places. But I'm talking about the cardinality of a set, so I'm talking about something that's a whole number, a natural number. So I want to say that n is less than or equal to 8. The largest that the cardinality could possibly be is 8, because then I would have 2 to the 8 is 256 lines in my truth table. If I had 9, then I would need 512 lines, and this would no longer work. And it looks like that will be the conclusion of our lesson, of this lesson on propositional logic.